Welcome to my presentation on the research project ABM for Energy Transition, agent-based simulation of energy transition pathways in urban environments. My name is Franz Mauthner from the Austrian Research Institute AEE INTEC. I'm part of an Austrian-Swiss consortium collaborating on this interdisciplinary project. Our partners include the University of Salzburg's Department of Geoinformatics, EPFL's Laboratory on Human-Environment Relations in Urban Systems in Lausanne, Switzerland, the front-end development team at Moving Layers, as well as the energy agency Styria and the municipality of Kapfenberg. The presentation is structured into three main sections. First, I will briefly introduce Austria's GELSEP initiative, which provides the spatial data needed for the agent-based model we developed. Next, I will delve into the ABM for Energy Transition project itself, its objectives, methodologies, and preliminary findings. This also includes a demonstration of the prototype ABM for Energy Transition WebGIS application. Finally, I will conclude with a summary of key points underscoring the potential of agent-based modeling for energy transition planning. Let's start with the GELSEP project, which stands for Green Energy Lab Spatial Energy Planning. The GELSEP initiative laid the groundwork for spatial energy planning in Austria, and its main output, the ENERGIEatlas, provides essential data layers for planning tasks in the energy sectors. We use this data to power our agent-based simulations. The ENERGIEatlas is a collection of spatial data layers used for analyzing buildings, existing energy infrastructures, and locally available renewable energy sources, all crucial for energy planning at local and regional levels. The image on the slide provides an overview, so it contains more detail than I can fully cover here at this point. However, key outputs include data layers for the heat, electricity, and transport sectors, now integrated into the federal GIS systems of Salzburg, Styria, and Vienna. The ENERGIEatlas is a significant step forward for spatial energy planning in Austria, but challenges remain. It's crucial to ensure that local authorities and planners actively use this data and that user-friendly tools and workflows are developed to integrate this data into practical planning use cases. In this context, the ABM for Energy Transition project aims to leverage spatial data from the GELSEP ENERGIEatlas to assess pathways for municipal heat and energy transition using an innovative agent-based modeling approach. Our goal in the project was to develop a tool that enables cities to explore energy transition scenarios and evaluate the impact of energy policy interventions on climate and energy targets. The ABM methodology therefore integrates spatial data describing the energy system in a study area such as buildings, grid-based energy infrastructure, and renewable energy potentials, with behavior models for agents representing homeowners, investors, or policymakers. The outcome is a map-centered web application with a dashboard presenting the ABM results. This allows users, for example, from public authorities or energy planners, to explore the impact of different energy policies and technical interventions. The dashboard provides insights into key metrics such as energy and life cycle assessments, technology adoption trends, or the distribution of heating supply technologies with adjustable spatial and temporal resolutions. As part of the project, we developed two distinct agent-based models. In a technical base model, building renovations and boiler replacements are driven purely by energy system characteristics, such as the age of buildings, existing heat supply infrastructures, and available renewable energy potentials. Technical input variables like renovation rates and preferred heating system technologies are used to simulate the changes. This model provides a technically oriented view of energy transition dynamics based solely on infrastructure and system attributes. In contrast, the behavioral model incorporates human factors, Building renovations and boiler replacements are influenced by the behavior of agents, which is shaped by their attitudes, social norms, and perceived contexts. Here we simulate the impact of various interventions, such as regulations, financial incentives, and information campaigns, on agent behavior and, consequently, on the energy transition outcomes. This model provides a more holistic view, integrating both technical and behavioral dynamics. Next, I will present a demo of the ABM for Energy Transition web application. This tool visually integrates the two models we have discussed. To start a simulation, the first step is to define the research area and assign a label to the experiment. In the technical base model, the user is prompted to set several input parameters. These include building renovation rates, quality of building renovations, boiler replacement rates, a ranking of preferred heating technologies such as heat pumps, district heating, or biomass boilers, construction rates for newly built buildings, as well as start and end year for the experiment. For the behavioral model, these input parameters are not directly set by the users. Instead, they are generated as outputs from the simulation based on agent behaviors. Users are rather asked to define interventions that influence agent behaviors, such as subsidies, regulations regarding building codes or heating systems, as well as social interactions. Once all input parameters are set, the simulation can be saved and started. The user's input is sent to a server where the backend, based on repost for Python, processes the model runs. Upon completion, the results are sent back to the front end for post-processing and visualization. Now let's look at the results. The study area, in our case Kaffenberg municipality, is displayed on a map accompanied by a dashboard on the left side that shows various relevant details. Different data layers and results can be filtered and highlighted for each annual time step. Depending on the user profile, either expert users, planners, or citizens, the granularity of the results varies from aggregated 1 hectare hexagonal grids down to the individual building level. Key results from the simulation and shown in the web application include CO2 emissions, heating energy demands, spatial distribution of heating systems and energy sources, as well as renovation states of buildings. For post-processing and analysis, all results may be exported either in spatial data formats such as GeoJSON, Shape, or GeoPackage, as well as CSV or Excel files. To end up, I want to recap the key points from the presentation. In the ABM for Energy Transition project, we successfully developed and implemented an agent-based model for heat transition planning at the city level. An extensive empirical study conducted with around 30,000 households, from which around 2,800 responded, provided valuable insights into the key drivers behind building renovation and modernization efforts. The behavioral ABM model integrates these insights into agent decision making, allowing us to simulate more comprehensive energy transition scenarios and assess the impact of various policy measures. Last but not least, significant milestones were achieved during this 2-year project, so further model refinements and validation are needed for broader application. All right. I hope you enjoyed the presentation and perhaps found some inspiration along the way. Feel free to reach out to me at the conference in Aalborg or connect with any of my colleagues from the consortium. You can also find some additional content in the PDF version of this presentation on the conference homepage.